back. Today we will be discussing few problems related to entropy. In the first problem, a completely reversible heat pump produces heat at a rate of 300 kilowatt to warm a house maintained at 24 degrees Celsius. The exterior air, which is at 7 degrees Celsius, serves as the source. Calculate the rate of entropy change of the two reservoirs and determine if this heat pump satisfies the second law according to the increase of entropy principle. So, in this question there is a heat pump which is reversible. It produces heat at a rate of 300 kilowatt. So, QH dot is equal to 300 kilowatt to warm a house maintained at 24 degrees Celsius. So, this temperature is 24 degrees Celsius. The exterior air, which is at 7 degrees Celsius, serve as the source. So, it takes heat from the exterior air which is at 7 degrees Celsius. So, heat taken from rate of heat taken will be QL dot. Calculate the rate of entropy change of the two reservoirs. The work input is rate of work input is W dot net. So, the COP for heat pump is TH divided by TH minus TL, considering it as a reversible heat pump. So, TH is 24 plus 273 divided by 24 minus 7. So, this is equal to 70.47. This is the COP of reversible heat pump. Now, the power required to drive this heat pump is W net and this is equal to QH dot divided by COP of this reversible heat pump, and this is equal to 300 divided by COP, which is 17.47, comes out to be 17.17 kilowatt. Now, the rate at which heat is removed from the low temperature energy reservoir is QL dot is equal to QH dot minus W net input. This is equal to 300 minus 17.17. So, it gives 282.8 kilowatt. Change in entropy of high temperature reservoir is delta S, or its rate is Q dot H divided by TH. So, this TH is 24 degrees Celsius. So, it is 300 divided by 24 plus 273 and it is 1.01 kilowatt per Kelvin. And rate of change in entropy of low temperature reservoir will be delta SL dot and it is equal to QL dot divided by TL. So, it is equal to minus 282.8 divided by 280. This negative sign is because the heat is being removed from the low temperature reservoir, that is why this negative sign is coming. So, it will give a value of minus 1.01 kilowatt per Kelvin. Now, the net rate of entropy change of everything in the system is, that is delta S dot total is equal to delta SH dot plus delta SL dot, and this comes out to be 1.01 minus 1.01 and this is 0. It satisfies the second law according to the increase of entropy principle. Moving on to the next question. Here a 25 kg iron block initially at 350 degrees Celsius. So, there is an iron block at 350 degrees Celsius is quenched in an insulated tank. So, this is a tank which is insulated and it contains 100 kg of water at 18 degrees Celsius. So, this is water and inside a iron block is quenched. Assuming that water that vaporizes during the process condenses back in the tank, determine the total entropy change during this process. So, taking all the contents of the tank as a system, so water and iron as a system, and applying energy balance, E in dot minus E out is equal to delta E of the system. Now, nothing is coming in and nothing is going out, so both are 0. So, 0 is equal to change in energy of the system will be equal to change in internal energy of the system. So, that is delta U. So, this can be written as delta U is change in internal energy of the iron plus change in internal energy of the water, and this is equal to 0. So, the internal energy change for iron will be its mass multiplied by the specific heat and the change in temperature. So, this is for iron, and similar expression will be there for water, mass multiplied by specific heat to T2 minus T1 for water. T1 and T2 are different for iron and water. So, we will put the corresponding values, and Cp for water is equal to 4.18 kilojoule per kg degree Celsius, and Cp for iron is 0.45 kilojoule per kg degree Celsius. T1 for iron and water will be different, although the T2 will be same for both as it is the equilibrium temperature. So, putting all the values in this expression, mass of iron is 25 kg, multiplying this by C of water or Cp of water. Mass of iron is 25 kg, Cp of iron is 0.45 kilojoule per kg degree Celsius, and T2 minus T1, so T2 is not known and T1 is 350 degrees Celsius. Similarly, for water, mass is 100 kg, Cp is 4.18 kilojoule per kg degree Celsius, and T2 is unknown minus T1 is 18 degrees Celsius, and this whole is equal to 0. So, from this equation we get T2 is equal to 26.7 degree Celsius. So, we have to determine the entropy change during this process. So, applying entropy balance, S in minus S out plus entropy generated is equal to change in entropy of the system. Now, S in and S out will be 0 as nothing is coming out and going. So, S gen or entropy which is generated is equal to change in entropy of the system. Now, change in entropy of the system is equal to change in entropy of iron plus change in entropy of water. The change in entropy of iron, this is equal to mass multiplied by specific heat into ln T2 by T1. So, this is equal to 25, which is the mass, multiplied by specific heat 0.45 kilojoule per kg Kelvin into ln of T2 as we have calculated previously divided by T1. So, this gives delta S for iron as minus 8.232 kilojoule per Kelvin. Similarly, change in entropy of water is equal to mass of water multiplied by the specific heat and into ln T2 by T1 for water. So, this is equal to 100 kilogram multiplied by 4.18 kilojoule per kg Kelvin into ln 299.7 divided by 291. So, this is equal to 12.314 kilojoule per kg. So, this will give S gen, which is equal to change in entropy of the system, which is equal to delta S iron plus delta S of water. So, minus 8.232 plus 12.314, and this is equal to 4.08 kilojoule per Kelvin. Moving on to the next question. In this, a well insulated shell and tube heat exchanger, so this heat exchanger is well insulated, is used to heat a water. So, Cp is given of water in tubes from 20 to 70 degrees Celsius. So, water is entering at 20 degrees Celsius and it is going out at 70 degrees Celsius. So, this point is taken as 1, this as 2. Heat is supplied by hot oil and Cp is 2.30 that enters the shell side at 170 degrees Celsius. So, this enters at 170 degrees Celsius from here. So, this we take as 0.3 at a rate of 100 kg per second. Disregarding any heat loss from the heat exchanger, determine the exit temperature of the oil. So, this temperature we need to find out, and the rate of entropy generation in the heat exchanger. So, this we mark as 0.4. We take the cold water tubes as the system. So, if we apply energy balance on the water tubes only, so E in rate of energy which is coming in minus rate of energy which is going out is equal to rate of change of energy of the system. Now, as it is a steady system, so this will be 0, E in dot is equal to E out dot. Now, rate of energy which is entering is Q in dot the heat which is added to the water plus the enthalpy of water m dot rate mass flow rate of water into enthalpy of water is equal to the net energy which the water is taking with itself when it is moving out of the heat exchanger. So, that will be mass of water multiplied by the enthalpy of water at 0.2. Now, the rate of heat transfer to the cold water in this heat exchanger becomes Q dot in is equal to m dot H2 minus H1. So, this can be written in terms of specific heat and temperature difference. So, this is m dot Cp of water multiplied by T out of water is T2 minus T1. So, putting all the values, mass flow rate of water is 4.5 kg per second, specific heat is 4.18 kilojoule per kg degree Celsius, and temperature difference is 70 minus 20 degree Celsius. So, this comes out to be 940.5 kilowatt. Now, we know that the amount of heat gained by water will be equal to the heat lost by oil. So, heat so, for oil Q dot is equal to mCp T3 minus T4. So, Q dot is known, we know T3, we know m dot and Cp all for oil. So, T4 is equal to T3 minus Q dot divided by M dot into Cp. So, this will give T4 is equal to 170 degrees Celsius, which is T3 minus 940.5 kilowatt divided by 10, which is the mass flow rate, and Cp, which is 2.3 kilojoule per kg degree Celsius. So, this gives a value of T4 as 129.1 degree Celsius. So, this is the exit temperature of the oil. The second problem is the rate of entropy generation in the heat exchanger. So, if we apply entropy balance on the entire heat exchanger, so it is S in, this is in the rate form, S in minus S out dot plus rate of entropy generation is equal to rate of change of entropy of this system. For a steady flow system, this term is 0. So, the entropy which is entering is mass flow rate of water multiplied by the entropy at point 1 plus, along with oil, the entropy which is entering is mass flow rate of oil multiplied by S3. Streams which are leaving, because of them the change in m dot water multiplied by S2 minus, because of oil it is m dot oil into S4 plus S dot gen. So, this is equal to 0. From here the rate of entropy generation is equal to m dot of water multiplied by S2 minus S1 plus mass flow rate of oil multiplied by S4 minus S3. And noting that both fluid streams are liquid and are quite incompressible substances, so rate of entropy generation is, so these expression, this and this expression can be written as m dot water. So, change in entropy will be Cp ln T2 by T1 plus m dot of oil Cp ln T4 by T3. So, putting all the values, mass of water is 4.5 kg per second, Cp is 4.18 kilojoule per kg Kelvin, ln T2 is 70 plus 273 divided by T1 20 plus 273 plus mass of oil is 10 kg per second, mass flow rate of oil is 10 kg per second, specific heat is 2.3 kilojoule per kg Kelvin, and multiplying this by ln of, so T4 is 129.1 plus 273 Kelvin divided by T3, which is 170 plus 273. So, this gives a value of S gen, which is equal to 0.736 kilowatt per Kelvin. So, this is the rate of entropy generation in the heat exchanger. Moving on to the next question. So, a steam enters an adiabatic turbine steadily at 3 megapascal and 400 degrees Celsius and leaves at 50 kilopascal and 100 degrees Celsius. If the power output of the turbine is 2 megawatt, determine the isentropic efficiency of the turbine and the mass flow rate of the steam flowing through the turbine. So, there is a turbine at point 1 here is at 3 megapascal and 400 degrees Celsius, and then steam is moving out at 50 kilopascal and 100 degree Celsius. Now, state 1, is superheated state. So, if we see from steam table for superheated water at 400 degrees Celsius and 3 megapascal. So, H1 is 3231.7 and S1 is 6.9235. So, H1 is equal to 3231.7 kilojoule per kg and S1 is equal to 6.9235 kilojoule per kg Kelvin. At state 2 it is at 50 kilopascal and 100 degrees Celsius. This is also a superheated state. So, at a pressure of 50 kilopascal which is 0.05 megapascal and 100 degrees Celsius. So, values are H 2682.4 kilojoule per kg and S2A is 7.6953 kilojoule per Kelvin. Now, we are representing this as H2A and S2A because this is the actual process, but in the question we need to calculate the isentropic efficiency of the turbine. So, if we see in the TS diagram, so this is T S, so corresponding to 400 degrees Celsius. So, this is the line and this is so this is for 3 megapascal and this is 400 degrees Celsius. This temperature is 100 degrees Celsius. So, this is 0.1 3 megapascal and so this is 3 megapascal and 400 degrees Celsius. Now, in the actual process it is moving like this. So, this is 0.2A, but for an isentropic process the entropy will remain constant and it will go something like this in a vertical. So, this is represented as 0.2S. So, here the S1 is equal to S2S. So, this represents an isentropic process. So, to calculate the properties at this point 2S, we know that this pressure is 50 kilopascal. So, P is 50 kilopascal and S1 is equal to S2S. So, at point 2S the pressure is 50 kilopascal and the entropy is equal to S1. For getting enthalpy at point 2S, so H2S, we know pressure and the entropy. So, if we see from the TS diagram, we see that this is moving into the vapor and liquid region where there is a mixture of liquid and vapor, and also if we see at 50 kilopascal from the table of saturated water. So, 50 kilopascal, if we see the values of the entropy for state 2S lies between these two values. So, it means that it will be a mixture of liquid and vapor. So, for this we can calculate the value of x at 2S. So, this is equal to S 2S is equal to SF plus X2S plus SFG. So, from here X2S is equal to minus SF divided by SFG. So, these values are known 1.0912 divided by SFG 6.5019 and this comes out to be 0.897. Now, as we know value of X2S, so we can also calculate value of H2S which is equal to HF plus H2S plus HFG, and this is equal to HF is 340.54 plus X2S, which is 0.897 multiplied by HFG, which is 2304.7. So this gives a value of H2S, which is 2407.9 kilojoule per kg. Now the isentropic efficiency of the turbine is given as H1 minus H2A, this is for the actual process, divided by H1 minus for the isentropic process. So all the values are known, so this will give 3231.7 minus 2682.4 divided by 3231.7 minus 2407.9, and this is equal to 0.667 or 66.7%. So the isentropic efficiency of turbine is 66.7%. In part B, we have to determine the mass flow rate of stream flowing through the turbine. So mass flow rate of stream flowing through the turbine can be determined from the energy balance of the steady flow system. So E in minus E out is equal to delta E of the system. For this steady system, this is equal to 0. So E in dot is equal to E out dot, and E in is equal to m dot H1 is equal to E out, which is work out plus m dot H2A. So work output is equal to m dot H1 minus H2A, and from this m dot is equal to 2 megawatt, which is the work output, divided by 3231.7 minus 2682.4, and this is in kilojoule per kg. And also for making units consistent, so 1000 kilojoule per second is equal to 1 megawatt. So this gives a mass flow rate which is equal to 3.64 kilojoule per second. So this is the flow rate of the stream flowing through the turbine. So we will end this lecture here. Thank you.